All right, so I'm going to give, I would say, down and dirty overview of general relativity. Didn't like the title that much. They're relatively unenlightened, but general relativity really comes in two flavors. There's a really complicated version, which has lots and lots of mathematics, which I absolutely adore. And then there's the other type, which is to try to encourage people to think about how general relativity defines the behavior of masses and light and space-time. So I'm going to kind of blend a little bit of that. I'm going to take a hint from Stephen Hawking. When he wrote Brief History of Time in his introduction, he pointed out that when he went to the publishers about writing this book about the nature of space-time, black holes, and all that, the publisher said, well, how many equations do you have in it? He said, well, does that make a difference? And he said, for every equation, you lose 10% of your audience. So I have 3 equations. So I'm going to lose 30%. That's fine with me. I have no problem with that. So let's start with the way you should start every presentation. You start with a little bit of humor you kind of add in. I'm a big fan of XKCD. This is probably the best way in which you can kind of outline it. I use this as a model, starting with understanding gravity and space-time. It's like a rubber sheet, massive objects distort the sheet, and then of course there's, because they're pulled down by what? And then of course you sigh and you say, well, space-time is like a set of equations, and at that point you kind of lost. I'm going to describe what space-time looks like using this model because this is Stephen Hawking's model over here, and I like it. And as a teacher, I steal from the best every chance I can. All right, so let's start with a little. Okay, well that's not. Next one, and it's technology. I hate technology. So it's not moving to the next slide, and that's happening. So space bar. It's a touch screen. All right, so let's start with background. I'm going to just touch screen this thing, I guess, to death. So Isaac Newton really was the first to try to unify concepts that had been around for 100 years. In 1543, Nicholas Copernicus developed the theory that instead of having everything in the universe orbiting the Earth, a geocentric system, he came with a heliocentric system where everything in the solar system orbited the sun. And then the distant stars were, you know, still very much the Greek model. They were firmament in the heavens and really weren't doing anything. After that, there were a handful of scientists, particularly Tycho Brahe and Johannes Kepler. Brahe was an observational astronomer, the last of the great naked eye observers, who very carefully mapped the heavens and in particular mapped the orbits of the planets. At that time, parts of Mercury, a good chunk of Venus's orbit, certainly Mars and Jupiter, and then some of Saturn. And as an amateur astronomer, if you spend any time outside, you know that Mars and Jupiter are up in the night sky more often than not. And so over the course of 20 some odd years, he had a really complete compilation of data about the location of the planets in the heavens. Unfortunately, he was not a particularly good mathematician, so he hired a young man by the name of Johannes Kepler, who in 1601 met with him. Brahe had kind of run away from Denmark and settled in Prague, and over the course of the next 2 years or so, he kind of hinted to Kepler that he had all this data, but he wasn't willing to give it to him because he was afraid that Kepler was going to undercut his model of the solar system, which was the Earth in the center, Moon, the Sun orbiting the Earth, and all the rest of the planets orbiting the Sun. Okay, the tectonic system is weird, but it was a nice, you know, compromise. And Tycho Brahe fervently believed in his system. I'm absolutely certain that Kepler didn't care because he was a Copernican through and through. So when Brahe died in 1601, the family of Brahe did not offer to give him that data as Brahe had promised Kepler on his deathbed, so Kepler stole the material and took off to Austria, where over the course of the next decade, he developed the Rudolphine tables, which is a series of planetary locations and star maps, and then more importantly began to work on what he called his war on Mars, which was to figure out the orbit of Mars. And over the course of a decade and then another decade's additional work, he developed the 3 laws of planetary motion. The first one is that planets orbit the sun in an ellipse, with the sun at one of the 2 foci, the 2 focus points. The second one is that planets sweep out equal areas in equal times. In other words, when they move close to the sun, they move fast. When they move far away, they move much more slowly. And the third one, which is the most curious one, was the square of the period is proportional to the cube of the semi-major axis. In other words, if your radius is the semi-major axis, you cube that, and that's proportional to the square of the period, which is a really weird thing because, well, for one, it didn't make a lot of sense. And Kepler, when he wrote Harmonices Mundi, where he described this discovery, he implied that a bird sang the song to him, and he realized that orbits follow this weird elliptical orbit, which made no sense. Galileo, who was also Copernican, didn't buy into the elliptical orbit idea. He still believed in circular orbits, but his approach was to try to describe motion on Earth, because motion on Earth was complicated and difficult to perceive. For example, the Greeks believed there are 2 types of motion. There was natural motion, there was violent motion. So natural motion meant if you took something and let go, it would fall to the ground. Natural state was the state of rest. A violent motion would be like taking an arrow, attaching it to a bow, releasing it, you've added something to it, and so to the Greeks, the arrow would fly in a straight line until it ran out of violent motion, and then it would fall to the ground. Now, if you've actually watched anything like that, you know it follows a curve, but the Greeks had this kind of weird vision of, well, I'm not going to actually experimentally confirm any of this, I'm just going to believe it. And that seems good enough for them. And Galileo said, well, no, we need to confirm this. And over the course of about a decade, Galileo showed that, in fact, objects move in a gravity field in a parabola. They follow a parabolic motion. Parabolic motion does not seem to match elliptical motion in the heavens, and so for all intents and purposes, there are 2 tracks to understanding motion on Earth and motion in the heavens. In 1666, Isaac Newton discovers a way of connecting the 2 of them together, and then he promptly doesn't tell anybody for 21 years. And in 1687, he published the Principia, where he explains that the motion in the heavens and the motion on Earth are exactly the same. It's just based on the gravity field and conic sections. And it creates a revolution in science. And it's absolutely fundamental to the way we teach physics today, because it's the foundation for all classical mechanics, which is about typically half a year's worth of typical high school, college physics. In Newton's case, the second law is force equals mass times acceleration, which basically says if I have a mass and I accelerate it, I have to apply a force to move it. So anything that moves has to be pushed or pulled, and that's essentially F equals ma, the second law of motion. In the Principia, he also pointed out that the force of gravity is equal to a gravitation constant, which in 1798, Henry Cavendish would calculate for the first time, times the product of 2 masses divided by the square of the distance between those 2 masses. And he assumed that this relationship was equal to that relationship, that gm1m2 over r squared is equal to mass times acceleration, which allows you to measure gravity. And that's a really incredibly important concept, because it says what happens on Earth is exactly the same thing that happens in the heavens. And part of the Principia, he proves Kepler's 3rd law of planetary motion, that planets do in fact orbit in ellipses. It's a very elegant mathematical proof. I usually do a proof of this in my physics class using circular orbits, but the elliptical orbit proof is a little more complicated, and usually it's introduced in a calculus class. So there is a possibility to see this in your mind, but I don't want to delve into the equations of it so much as to say, Newton said there are 2 things that we assume are equivalent. In other words, the force of gravity in space and mass times acceleration on the surface of the Earth. And that works. It seems to work pretty well across the board. All right, so that's the background to much of this. We need to have that in place. And then along came Albert Einstein. So Einstein, as many of you sort of know, I would assume you reasonably know, was kind of the leading light of physics in the early 20th century. And in many respects, he was pretty much an average student. He went to the ETH, which is equivalent to the Swiss Institute of Technology, graduated with a degree in physics, went on to work on a PhD, and in 1905, he published 4 incredibly important articles. One of them described Brownian motion, One described measuring the size of an atom. A third one which described special relativity, which has to do with motion close to the speed of light, which I'll reference a little bit tonight. And the fourth one was the photoelectric effect, which is the foundation of quantum mechanics. And that sort of put him on the map, but not the way he expected. It would take another 5 or 6 years before he was actually offered a research position with the Russian Academy of Sciences, primarily because he was a patent clerk at the time, and he really didn't see any aspirations. He wanted to be in a university. That really wasn't available to him. He thought these articles would make him famous. They sort of made him well-known among physicists. And then Max Planck, who was one of the early 20th century quantum mechanics physicists, kind of led us into this path, offered him a position as a research scientist at the Russian Academy of Sciences, where from 1910 to 1915, plus 3 years in advance, he was working on what we today call the general theory of relativity. And I kind of want to go through on how he got this. He was working at the patent office in Bern at the time, and he always read the paper in the morning. And one of the newspaper articles talked about how a house painter had fallen off the scaffold from 3 stories up and crashed into some bushes and broke his hip and a couple other things. And Einstein said when he read that, it really hit him that if you fall, you don't feel your own weight. That's a really subtle concept, because we think about gravity as pulling us down. You know, we feel that at the end of the day, because if you've been sitting in a chair all day, your butt hurts. If you're standing around all day, your dogs are screaming. And the main reason is because we think we feel gravity. But if you fall out of a window or you fall off an airplane, you know you're falling because you feel air rushing past you. But if you were in a vacuum, you would have no idea you're falling. You'd be floating for all intents and purposes. And in that point, Einstein said, well, wait a minute. If I don't feel anything, how can that be a force? Because a force is a push or a pull, and I can feel those. And that made a great impression on him. Unfortunately, his mathematical skills were not really at the standard that most physicists and mathematicians believed it needed to be in order for you to solve this. He had a competitor by the name of David Hilbert, who actually knew a lot of the mathematics, but didn't have the physical insight into solving this problem. And so for 8 years, Einstein kind of worked through this, learned some new math, had to relearn some old math, and had to apply these ideas into this kind of polyglot of concepts that he could then summarize as what we today call the equations of general relativity. This is a model, and there's a lot of subtleties involved in it, which I'm not going to go into, but it's important because it makes some really important predictions that we can now experimentally confirm. Okay, so the first one's the principle of equivalence. And the principle of equivalence basically says that acceleration is exactly the same as gravity. There is no difference between the two. Okay? And because of that, that implies that an inertial mass, a mass related to F equals ma, is exactly the same as a gravitational mass. That's something that Newton believed, and Einstein just said, okay, if it's true, I'm going to assume it is. Now what happens as a result of that? And what that implied, it led into an accelerated frame of reference. Let me give a very simple kind of geometric argument for this. You're standing in an elevator, and there's a hole in the elevator that allows a beam of light to pass through, okay? And the elevator is going to accelerate upwards. So in the first moment of acceleration, you're going to move a little distance. The second moment, you're going to move more. Third moment, you're going to move more, because as the velocity increases linearly, the position increases exponentially, a power function. And so as a result, if I plot the location of that beam of light, we're slow enough, as I'm moving up in the elevator, the beam of light would follow a curved path. In other words, if you're an elevator accelerated upwards, light curves in that accelerated frame. And then Einstein said, well, no, I'm lying to you. You're in a gravity field. Gravity acceleration is the same. So in other words, light bends because of gravity. Gravity and acceleration have to be equivalent in order for that to occur. So in this case, if I have a spaceship that's accelerating upwards, light's going to curve in that path. If I'm sitting on the surface of some planet, it has to do the exact same thing. So in an accelerated frame of reference, gravity, moving, doesn't make any difference. Light's going to bend along the path. And that really describes what happens in an accelerated frame, which leads into a gravitational field. In other words, gravity is geometry. Changes the way we see gravity. It's no longer just force pulling and pulling on you. It has to do with the geometry of the space and time you're standing around. Special relativity is just a special theory which says, I'm going to make a special condition, acceleration equals 0. What happens when you go really fast? Not as you accelerate up, what happens when you're traveling really close to the speed of light? If you travel close to the speed of light, time slows down, length contracts, mass goes to infinity. Because we can't have enough energy to make something go the speed of light, anything that has mass can't go the speed of light. It's limited by the speed of light. It is literally the speed limit of the universe. Nothing expands faster than the universe, which is expanding at the speed of light or near it. So as a result, Einstein took this inertial reference frame, something moving at a constant speed, and generalized it into an accelerated frame, which is now a general theory of relativity, as opposed to a special case of relativity. Okay, so in other words, it's the curvature of space-time. Space-time is curved. And John Archibald Wheeler, who was one of America's great 20th century physicists, said, mass tells space-time how to bend, and space-time tells light how to move. Okay, I'm going to do a very simple geometric model that's very similar to the cartoon at the very beginning. And I'm going to summarize in just a couple of steps. Let's assume the room has a special type of rubber sheet that's spread all the way across the room. It's tightly bound on the walls, so it's perfectly flat. There's nothing on it. It's perfectly flat. Now, it's a special rubber sheet because I can walk through it. Okay? And so what I do is I take a BB, which represents a particle of light, and I place that BB on the sheet, and I flick it towards somebody and give it a little whip, and I make it travel in a straight line. So this path is always going to be a straight line, and the reason is very simple. There's no other forces acting on it. It's traveling on a flat surface, so it's going to follow the law of inertia. It's going to go in a straight line, constant velocity, until it runs into something. All right, now what I do is I take a baseball and I put it somewhere in the middle of the sheet. And I take that BB again, I've got an infinite number of them, place it on the sheet, and I flick it off to the corner. What path does it take? All my physics students back there know what I'm talking about. A straight line. It doesn't feel that curvature. A baseball doesn't have a lot of mass. So for all intents and purposes, it's still a straight line. If I flick the BB close to the baseball bends the sheet a little bit, and so it might bend a little bit, but only if it's going very close to the baseball. All right, so I remove the baseball, I put a bowling ball in the middle of the sheet. If I flick a BB in this direction with a bowling ball over here, it still doesn't bend much because it's not bending the sheet dramatically. But if I take that BB and aim it closer to the bowling ball, but further away from the baseball, it will then curve more dramatically. And in fact, it'll curve in a nice hyperbola or a parabola or even an ellipse and stay in orbit that way. And then if I'm really clever and I take that bowling ball and squeeze it to a really, really tiny volume of space and put it in the same spot, it'll bend the sheet to a really dramatic depth. And that BB could actually circle around and eventually kind of fall into it, kind of like those little graviton toys they have at museums and in the mall, where you put coins in it and you let it go around and around and around. My wife will understand when I say this. When we go to the mall, all she has to do is give me a couple of rolls of pennies, a buck's worth, and I'm entertained for 3 or 4 hours because I'm standing there rolling pennies down opposite each other, one right after the other, 2 together, all kinds of interesting calculations, watching the pennies roll along until they fall into the little hole. And the only problem is when little kids come up to do that, my reaction is actually, pretty subtle. It's like, get away, I'm doing physics. I'm my thing. So she could shop for several hours and I'm entertained for several hours by doing physics. And the reality is that's kind of what's going on here with this curvature of space-time. That Stephen Hawking defined it this way, described it this way, and we take that idea and we say, yeah, take a rubber sheet, put a mass in it, it bends it, and now that the path of a BB of light or any object that's moving around is going to follow the curvature. And so therefore gravity, it's not really a force. Gravity is really just a measure of how much curvature you have. So to a physicist, if you say, well, how much curvature is around the Earth? I would say, well, at the surface of the Earth, the curvature is about 9.8 meters per second. Whereas if you're standing on the moon, the curvature of space-time around the moon is about 1.7 meters per second, which is a geometric measure of curvature. And that's really what we're attempting to think about in our heads. All right, so with that in mind, let's look at an equation. Okay, I just lost another 10%. I'm on my way. All right, so this is the Einstein field equation. GUV plus this upside down delta GUV is equal to 8 pi G over C to the fourth power DUV. Okay, these are tensors. Tensors are, in the simplest sense, they're multi-dimensional vectors. And so in this case, I've got 4 dimensions that's built into this. On the left-hand side, we have what's called the Einstein tensor. We have this thing called the cosmological constant that Einstein kind of crammed into this model so he could explain stuff that turned out he was wrong, and then he took it out and we put it back in. We have the metric tensor, which basically kind of explains how things are put together. And then the right-hand side, we have what's called the stress energy tensor. So the right-hand side describes all the mass and energy in the universe. The Einstein tensor describes the curvature of space-time. And then this metric tensor with this little constant describes expanding universe, sometimes referred to today as dark energy. All right, now that's for the math people who really like it, they're going, okay, I got it. Yeah, this is really exciting. For the non-math people, I put it in a simpler context. So, everything on the right-hand side, stuff. Everything on the left-hand side, it's a shape of space-time, and then how the shape is changing space-time. And if I think of it this way, this is all the stuff that's in the universe. And then here's the shape of the universe based on the stuff we have in it. And then this little metric tensor describes how the shape of space-time changes. I can kind of visualize very simply the geometry of space-time. So what this implies is if I've got a lot of stuff, the curvature, that's the shape, is going to be big, and it's going to evolve slowly. If I have a little bit of stuff, the shape is not going to be as dramatic. It'll be flatter, but it can evolve more quickly because in this case, I don't have a lot of stuff holding back, and it's not being warped into space. Okay? It's fundamentally, conceptually, it's really a pretty simple idea, but it takes a little kind of beyond what we're used to because we live in a world which is very dramatically shaped by Newtonian physics. Gravity is a force, it's actually acceleration, it pulls me down and makes my feet hurt, my butt hurt, but for the most part, I live in a world that, is very straightforward and very simple. And the Einstein field equation says, well, it's not quite that simple. There's a lot of subtleties built into this. These are computationally very difficult to work through. We've explicitly solved only a handful of them. There are fundamentally 10 equations built into this thing. We've only solved a few of them explicitly, a couple of computations. There's a few that haven't yet been solved. And we're playing with it because this is how we do this kind of stuff. We want to describe how the universe works. And this right now is the equation that kind of leads us in the direction we're going. And the reason I know that is because there's a lot of evidence that it works really well. So let's go through some of them. So the first one is astronomers jumped into this immediately. And the reason is there were 2 things they were looking for. The first one was to describe what's called the precession of Mercury's orbit, which I'll describe in a few minutes. And the other one was we wanted to confirm the idea that space-time is curved by looking for starlight's path being bent by an eclipse, which in 2024, if you're really good, you know what you're doing, 6 months in advance, you go out and photograph the night sky where the eclipse is going to be with a very good telescope, very powerful telescope. You repeat that and you have clear skies during the day and you photograph that section again, look at those stars, you can replicate this experiment, which has been done several dozens of times since then. The first eclipse that did this was observed in 1919, and then we verified it in 1922. And so let's go through these 2 pieces of evidence. The first one is Mercury. So Kepler's third law of planetary motion, the first law says that planets orbit the sun in ellipse, and this path that Mercury is following is an ellipse, but it precesses. In other words, it moves off of the line. So its original path should follow this path here, but Mercury kind of moves sideways. It kind of does a spirograph thing. Now, there were arguments as to why it could do that. Most notably, Urbain Le Verrier was the first, and Simon Newcomb came up with another version of this thing in the early 20th century. They very carefully plotted using a process called astrometry, which is measuring the location of planets relative to the background stars. And they said, okay, the way this is happening is because other planets are pulling on Mercury. And as the other planets in the solar system move around, they're pulling on Mercury, constantly tugging it and making it move off center. And that counts for a lot of it. But there was enough missing enough of an error that they said, well, the only other way we could have this behavior is there must be another planet inside of the orbit. And so for nearly a decade, they searched for Vulcan. All the Star Trek people were like, did they find it? And the answer is no. There's no planet inside the orbit of Mercury. When Einstein published the general theory in 1915, astronomers looked at it and said, wait a minute, this accounts for the curvature of space-time near the sun. Let's see how that affects Mercury. And it turns out it predicts it by 43 arc seconds per century, which is almost precisely how much precession Mercury was exhibiting at the time. And that's an incredibly strong piece of evidence to an astronomer. But physicists believe in experimental evidence, and they said, well, there could be a lot of other things going on. You might have had another planet hit it, like it hit the Earth to make the moon. You might have other weird things happening. There might be not one big planet like Vulcan. It might be a series of small asteroids that are affected. So until you can do an experiment, I'm not so convinced. And then along came Arthur Eddington. So one of the key elements of the curvature of space-time is if you have a really large mass like the sun, and you've got between the Earth and where the actual star is located, the path of light from that star is going to be bent around the sun. And that's a prediction that Einstein clearly made, and Arthur Eddington calculated, and he said, you know what, I'm going to prove that. So on May 29th in 1919, right after World War I, he went to the Canary Islands and the west coast or east coast of Brazil, and they took photographs, not very many, but they got a few photographs of where the stars were supposed to be in the night sky 6 months later when the sun was being blocked by the moon during a total solar eclipse, and saw that change, that corroboration. He was predicted to have 1.75 seconds of arc, which is really, really tiny. So to give you a sense of that, if you hold your finger out at arm's length, this is about 1 degree wide. So divide that into 3,600 pieces, and it's 2 of those. So if you divide that width by 1,800, it's about 1/1800th of the width of your finger. That's how it was off. And that's incredibly subtle and very small. And despite the fact that Eddington said, look, this is really obvious, and informed Einstein in November of 1919, it wouldn't be completely verified until W. Campbell did it in Australia in 1922 and showed that, in fact, those values were correct. And as a result, it made Einstein absolutely famous, which is very strange, because if you've ever seen pictures of Einstein, he doesn't look like a famous guy, right? He's kind of a wild-haired old guy who kind of smiles, sticks out his tongue at the camera on occasion, and he studies things that make no sense to the vast majority of people, but it absolutely made him famous. In fact, by the early 1920s, there was only one person in the United States, around the world, who was more famous than Albert Einstein. Charlie Chaplin. He was a movie star. And Einstein was not, but he was considered one of the greatest scientists of all time. Yes, brilliant scientist, no doubt about it. General relativity is his baby. But if you think about context, in 1919, we were a year removed from World War I, a war that was primarily between France and England and Germany, and an English scientist corroborated the results of a German physicist's ideas about the nature of space-time, overthrowing Isaac Newton's work that had been around for 250 years. I can see why he's famous. In context, that's an incredible feat, and more importantly, it clearly shows that physics transcended conflict, borders, and nationalism, which is why he was famous and remained famous until his death in 1955. All right, so from there, what else do we do? Well, curvature of starlight is something we look for all the time. We see lots of examples. This is, on the left is an image of the Hubble Space Telescope. As we heard in the January meeting, the power, the magnification of the Hubble is almost exactly that of the Webb. The difference is the Webb looks in the infrared, it's a little bit, more precisely aligned. But if I look at these images, I can see some really subtle structures right here. If I look, I see curvature of things all the way around. I see the curvature of space-time. I see light being bent in a curve. And if I look at the Webb, I see it here, and I can see that there must be a large mass somewhere in here that's bending all of these, all the light from these galaxies into curves. We see it all the time. gravitational lensing is a fundamental way of showing that general relativity works. But that's not all we can do. There's a lot of other things we can look at. By the way, all of these you can find, you can astronomical picture of the lay and all that kind of stuff. Frame dragging. Frame dragging is really fast. I always thought this was one of the cooler things that we observed. In 2004, we launched a thing called the Probé B, which was basically a spacecraft that was 642 kilometers above the surface of the Earth in a nearly perfectly circular orbit. And it had an internal gyroscope that was lining up in one particular direction. As it moved, you would get what's called geodetic precession, cause it to kind of rotate, kind of like a spinning top would rotate a bit. And according to Einstein's general theory of relativity, anything that's sitting in this space as it moves around it is going to begin to create precession. It's going to start to wobble as it moves through space-time because it's running onto the surface of space-time. And so the predicted value of 39.2 minutes apart per year was confirmed to about 37 plus or minus 7 minutes of arc per year, which is an incredibly accurate measure for a satellite that spent a year in orbit and measured really subtle changes as it moved in orbit around planet Earth. And since then, we've had 2 other satellites that have done very similar things, and all of them confirming Einstein's general theory of relativity. Black holes, okay? I can go into an entire lecture on black holes all by itself, but I ain't going to because that's another talk, which I already gave you. Karl Schwareschild was the first to actually calculate what happens if you curve space-time enough that light can't escape them. And he didn't call these things black holes. He called them compact objects. So a stellar core, when it blows off the outer shell, can become so compact that light cannot escape its surface. We've described these before. John Mitchell and Simon Laplace in the 1700s both theorized that you get dark stars made out of really massive objects, but they would be big. These would be smaller. It would be the core of something that just crush itself down to the smallest size possible. There were scientists, Arthur Eddington for one, and Robert Oppenheimer, who actually published an article about this kind of compression, who absolutely did not believe these things existed. They were completely against it, and Eddington was aghast that even the idea would be proposed by anybody because it just seemed so bizarre. Nature doesn't make things that you can't see into. Nature doesn't make things that are invisible, and yet nature seems to. Some people, like John Wheeler, Charles Misner, Kip Thorne, Roger Penrose, and of course Stephen Hawking, became famous by examining these kinds of structures. What happens when you bend space-time? What happens when you let space-time warp so dramatically because of these compact cores, and the result you get what we call a black hole. And they are the strangest astrophysical structure in the universe, and that's incredibly complicated, but it's got some really simple, subtle aspects that we can at least describe briefly. So the first one is black holes only have a few distinct properties, which make them very unique. They have to have a mass. The mass of the black hole, the object that makes the black hole called the singularity, has to be at least 3.2 times the mass of our sun. So our sun's never going to make a black hole, make a white dwarf, but it's not going to make a black hole. It can never make a black hole. It's not nearly big enough. The second thing is it can have spin. It doesn't necessarily have to have spin. They probably all have spin because everything in the universe spins. And so eventually, as it blows off in our shell, it spins faster. So it's got spin. It can have an electromagnetic field. And the evidence is black holes probably seem to have electromagnetic field because there's lots of evidence that they have these big, powerful magnetic fields associated with them. And they can have a temperature. Although the temperature is very, 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 very small, this is what Stephen Hawking was most famous for. He calculated what the temperature of a black hole is and how it gives off energy over time, and eventually the black hole evaporates. And that's it. Those are the 4 primary properties that black holes have. And since temperature takes really billions of years to occur, maybe even trillions of years, the only 3 things we look for in black holes is it has to have the right size, it has to have a spin, generally, and it probably has electromagnetic field. In other words, black holes have no hair. They're just there. And that's all there is to it. And by the way, this image here is actually a model that was used by Kip Thorne and his group of graduate students for the movie Interstellar, because we use that as part of the key element of it. So there are, in fact, 4 types of black holes that come in 4 flavors, if you will. the Schwareschild black hole, Reisner, Nordstrom, Kerr, and Kerr-Newman. And I'll just briefly talk about each one and just kind of move past it. Schwareschild are static black holes. When I was an undergraduate student in my general relativity course, we actually solved the equation for a Schwareschild black hole. It's stationary, nothing's happening, boring, easy to solve. Okay, the metric's very simple, a couple of pages of calculations, and voila, you know all the things you need to know about it. It says it doesn't do anything, it just sits there. Reisner Nordstrom are black holes that have electromagnetic fields. So instead of having just an event horizon where things can't be seen, once you cross in the event horizon, you can't see out of it. I mean, you can't see into it, you can see out. It has two of them. There's a Cauchy version and it has a Schwareschild version, but you can't see the innermost one. So, you know, again, they're static. It's just a nice little electromagnetic model. Roy Kerr was a physicist, a New Zealand physicist who at Wright State University under appointment with the U.S. Air Force was calculating, you know, spinning structures, and he came with a computational model of a spinning black hole and published that. And then a year later, with his graduate student, he and Newman put together an electromagnetically charged spinning black hole that creates a big electromagnetic field. And now we got pictures of it, polarizing light and the whole thing. Most physicists today believe that only Kerr and Kerr-Newman black holes exist. A supermassive or Kerr or rotating black hole was the key component in the 2014 movie Interstellar. So if you saw it, there's that scene where they're flying past and flying out of it, very exciting. Age, 51 years passes for the, few hours it takes to fly by. Very exciting. And on this image right here, this is the metric that's used to describe electrically charged black hole, which is complicated and unnerving. And quite frankly, I didn't enhance it because I don't want to lose 40% of the audience. At least that's the intent. Okay, gravitational waves. I need to talk about this a little bit in a couple ways. Fluctuation of space-time. In other words, if you think about it, space-time is in fact this rubber sheet, and I bounce on it. I can send a waveform all the way around. Okay? Kind of like if you jump on a bed, bounce, and jump on a trampoline to bounce. Same thing. Space-time does the same stuff. And the idea was people like Charles Misner believe that if I have two big objects that are rotating around each other, they'll eventually slide into and collide, they'll kick out a whole bunch of energy. But gravitational waves are very subtle and very hard to measure, and we've been trying for close to 40 years. In September of 2015, the LIGO, the Laser Interferometer Gravitational Wave Observatory, one's located in Hanford, Washington, the other was in Louisiana. They work as a collaborative pair, announced that they had discovered the collision of two black holes merging into one. One black hole about 29 times the mass of the sun, the other one 36 times the mass of the sun. And the gravitational waveform you see gets really large, it chirps, and then the black holes combine into this little form. And so they settle down and it sends out this big shock wave, which by the time it reaches us, because these are millions of light years away, we wouldn't hardly feel it. Now, the reason this is important is because in August of 2015, my wife and son and I flew out to Richland, Washington, where my brother-in-law works worked at the Hanford site before his retirement. And he said, look, LIGO's open this weekend. Let's go take a look. So we drove out, which is like 40 miles outside of Hanford. And we took the tour and we walked in the control room and all these people were working away, collecting data. And when I read the article about when they discovered it, it happened the weekend we were there. So I have a direct personal connection to gravitational waves. I'm not completely convinced, but reasonably convinced that if I hadn't been there, they never would have discovered them. So maybe you should name them after me, but that's just me. Time dilation. So time dilation comes in two forms. The most common one that we talk about is the special relativity. You travel really close to the speed of light and time slows down. So light itself travels, you go outside, you look at the Andromeda galaxy, which is 2.5 million light years away from us. A little photon of light that left that galaxy hits your eye. It's traveled 2.5 million years from our perspective, but to that little photon of light, it did it instantly. No time travels, no time changes, there's no internal clock for photons of light. They don't have any mass. However, it also occurs if you have a non or very slowly rotating symmetrical body, and you can measure it with respect to the center of mass to the position of the clock. And the reason this is important, it's very subtle, you don't really measure it much, but the reason it's important is because all of us who rely on GPS, which accounts for all of us, we actually have to program the global positioning system, satellites, and the receivers to take into account gravitational time dilation. So the receivers, the transmitters, satellites, are accurate to about 14 nanoseconds of error. And most of your receivers are accurate to about 100 nanoseconds. And the difference between the two is so small, it's very subtle, you wouldn't notice it. Although it does show up in a few places, because on occasion, a Google map, which uses GPS, has told people to make a left turn into a lake, because there are subtle changes and you need to have so many GPS satellites to line things up properly. Back in the 1980s and early 90s, when we launched these things, they were primarily launched for the military. So military units could keep track of where they were. GPS receivers could be purchased by the civilians, but they were incredibly inaccurate, accurate to about 100 square meters. And now GPS satellites, the GPS links in your phone, in your car, are accurate to about 9 square feet. So if you go out and you find a little tile out here that's 1 square foot, and you stand in the middle of 9 of them, that's how accurate we can tell you where we're at on the surface of the Earth. And the new GPS system that's currently being transitioned into by the Department of Defense will be able to measure that accuracy to 1 square foot. And that'll be online somewhere around 2035, 2036, which means we can keep track of where you're at to 1 square foot every moment of your life. That's why I turned my GPS off in my phone. Nobody's tracking me. Okay, wormholes. All right, wormholes are kind of cool because there's all this cool speculation about the nature of wormholes. In this case, if I were to take space-time and warp it and punch a hole in it, then I could create a wormhole. Okay, and that's actually a very fundamental part of Chris Nolan's movie Interstellar, is they fly through a wormhole into another galaxy where they're near a black hole and they explore these planets and all this kind of stuff. And there's a really nice scene where a guy named Romley is showing Matt McConaughey, Murph, how this works, or Cooper, how this works. Takes a sheet of paper, he draws an X at each point, draws a line, he says, if I fold over and punch a hole, guess what? I can go from one to the other without having to go the long distance. And then when you hold up, you have a hole, a wormhole. But wormholes are really three-dimensional. So in this case, it's actually a spherical structure, a spherical hole. And part of the plot was they fly through one of these wormholes. When Kip Thorne spoke at Grand Valley State University several years ago, that my son and I attended his talk, he talked about how, this would actually happen. You would enter a wormhole and you'd pop out if the wormhole was stable. There's not very many forms that can be stable. The Lorentzian wormholes appear to be stable without having any kind of exotic energy or some special rule applied. But if they do exist, they're incredibly rare and be very, very difficult to maintain. But it was a nice part of the story with one exception. If you enter a wormhole, when you enter the wormhole, you exit it at the exact same moment. That's because wormhole represents zero-dimensional space. So if you enter, you're coming out the other side. So imagine if I have a hula hoop of a wormhole here and a hula hoop wormhole over there, and I put my hand in it, my hand would disappear in this one, but you'd see it coming out at the exact same moment on the other side of the room, crossing this interdimensional space with zero time and zero effects. In the movie, they fly through it, the spacecraft rattles, they get to meet some aliens, which turns out to be Matthew McConaughey coming back. This was a weird movie. And then it takes time. In reality, it would be instantaneous. You fall in, you come out in no time at all, and then you'd be another part of the universe, the galaxy, and so on and so forth. It's a cool effect. I mean, this is a really nice special effect in the movie. Always makes me kind of happy to see it happen, but I know it doesn't really work that way. Dark matter. Dark matter is weird. In 1980, Vera Rubin, who was at the Carnegie Institute in Washington, D.C., as an astronomer, was plotting rotation curves of galaxies. So if I have a galaxy and it's spinning, then the arms of the galaxies you can see here, of this kind of whirlpool design, it should spin with a certain rate. And that rate follows a Newtonian curve. And so since most of the mass of the galaxy is in the middle, there's less on the outside, Objects on the outside should move slower than objects near the middle. So you get this Newtonian curve looks like this. But in 1980, Urbain and another handful of collaborators discovered the curve looks like that, which tells us there's something missing. There's more mass in the center of galaxies than what we can see with visible light. And for about 20 years, it was this constant, well, it's brown dwarfs, it's really supermassive planets like, 10 times the size of Jupiter, which isn't quite a star. There's a lot more dust and gas in these places, but every time we try to look for those things, we never saw anything like that. And so most scientists believe that there's some type of exotic matter that exists in the cores of really large clumps of stars, galaxies, that add mass to it to make that curve different. But we don't have any idea what it is because, unfortunately, general relativity doesn't tell us what it looks like. It just says, look, if this did apply, it would act like a bigger mass, and so the curves would make sense, but we don't have any idea what it's like. So we have all kinds of weird theories about what it is. When I worked at Notre Dame a few years ago, we had a physicist talk about dark matter, and he said if you put 100 physicists in a room and ask them what's dark matter, you're going to get 120 different answers because nobody knows and then nobody agrees on any of it. And then the worst thing of all is dark energy. In 1998, two groups, one from France, which I kind of understand, but one from Harvard, which makes me very angry, looking at supernova data of supernovas really far away, discovered that light function doesn't match what's predicted by a uniformly expanding universe. In fact, it's an accelerating universe. And in 1998, that was an enormous discovery that would lead to a couple Nobel Prizes. And for 24 years, 25 years now, we've been trying to figure out what dark energy is. And I can tell you in 3 words exactly what it is. We don't know. It acts like negative pressure. So if you think about a balloon, positive pressure is pushing the balloon out. This is negative pressure. Something's pulling the balloon out. So that's weird. We don't understand it. There's no even reasonably cogent theory explaining it. We don't even know how to ask the right questions, let alone what questions we want to ask. And there's absolutely no evidence that anything's happening that we can't perceive. There are physicists who, again, argue, well, maybe there's multiple parallel universes interacting with us we can't see. Maybe there are these brains, these membranes of space-time that, interact with our brain, and that causes it. We don't know. We have no clue, okay? It's completely up in the air, but it's really awesome because it keeps us employed. And I think that's, pretty important for most physicists. And then the real question is, where do we go from here? So one thing we'd like to do is we'd like to combine, like to marry general relativity, which measures and describes the universe as a big thing, with quantum mechanics, which describes the universe at the most subtle and smallest structures. So the interior parts of an atom, quarks, and electrons and neutrinos, the little pieces of matter that are connected to the larger pieces of matter that we create atoms and molecules from. That's quantum mechanics. It's driven by probability. It's very strange. It's lots of math, and it does make a lot of sense. Oh, by the way, some of them are talking to you. They wanted to, but it doesn't have a lot to do with astronomy, so probably not. Although it does have a lot to do with some part of astronomy, because every one of you here in this room, I assume, has a cell phone. Am I right?
God, no.
Yeah, well, one person doesn't, but everyone else. Your cell phone is a quantum mechanical device. The cell phone camera is a quantum mechanical device. It takes pictures of objects and it sees it as particles of light. And then it transcribes that information onto a charge-coupled device, a small chip, which then when you send it out by electromagnetic waves, sends that information out. So in other words, the picture is both a wave and a particle at the same time. That's quantum mechanics. How can something be a wave and a particle at the same time? Easy. You just have to say it's not what we're used to describing. And it's, again, very complicated. But tying that in, which is, the universe is very small, with the universe is very big, general relativity is really hard. And we've been at it for close to 50 years, probably longer, and we're nowhere closer now than we were 50 years ago. So we're kind of stuck. But, that's all right. Because after all, as I said, keeps us employed. And more importantly, if we can do this, we can somehow blend them together, which unfortunately, because of separation of scales, is very, very hard. Maybe we can make modifications to general relativity that does this. it's my personal belief, as somebody who spent 40 years of his life teaching and spending an awful lot of that time studying physics and long before that, is that the mathematics that's going to describe how general relativity is connected to quantum mechanics hasn't yet been put into physics context. I personally believe that that math has been discovered, but we don't know how to use it yet in physics. And the reason I say that is because in the early 1800s, there was a mathematician who developed a theory of group theory and sets. In other words, if I have so many seats, how many are filled, how many arrangements can I make of the way the seats are filled together? And set theory is really kind of complicated and interesting, but it really doesn't have an application. There's no real good application for it. And so it was kind of forgotten. It was kind of ignored until the 1950s, when people like George Zweig and Murray Gell-Mann fell back and discovered group theory can help describe structure of subatomic particles like protons and neutrons. The same thing has applied over the last 100 years. G.H. Hardy was a mathematician in Great Britain who wrote a book called A Mathematician's Apology, which kind of explains what he saw mathematics like. And he said, my greatest accomplishment as a mathematician is I've done nothing of value. All the math I've worked on does not help anybody. It doesn't hurt anybody. It doesn't do anything of any value whatsoever. That's my greatest accomplishment. Okay, 75 years after that, we started using a lot of his mathematics, particularly fuzzy logic and probabilistic systems, to develop keypad systems, to develop PIN numbers for ATMs. The NSA uses it for coding and breaking codes. I'm convinced that G.H. Hardy is spinning his grave right now at several thousand revolutions per second, because all the math that he built that had nothing to do with anything is now being used all around the world by bankers and CIA and NSA and government agencies, because it's math. And I'm convinced that this is going to happen at some point. I personally think the math that will describe this future is there. We just haven't quite figured out how to use it yet. But it's coming. And then if I start with a cartoon, I should end with a cartoon. Fundamentally, this is what physics is really all about. Imagining is fun.